Okay, get this. Have you ever seen a solid object just change its color on command? I'm not talking about paint. I'm talking about a tiny, invisible zap of electricity. Today, we are diving deep into the science behind one of the coolest materials that can do exactly that, a pigment called Prussian blue.
So here's the big mystery we're going to solve together. How on earth can a solid crystal basically perform a vanishing act? It goes from one of the most intense, deep blues you've ever seen to almost completely transparent. I mean, it really sounds like magic. But as you're about to see, it's all pure, fascinating chemistry.
All right, so to figure out how the color disappears, we first have to get why it's there to begin with. So our first stop is to uncover the secret of the blue.
So the secret, the real magic, it's all in the atomic layout. Inside Prussian blue, you've got these really special pairs of two different kinds of iron atoms. They're called iron 2 and iron 3, and they're distinguished by their electrical charge. Now, these two atoms are connected by this tiny little cyanide bridge, and this specific structure, well, it's the key to everything.
You see, this unique pairing allows for something called intervalence charge transfer, or IVCT for short. Now, the easiest way to picture this is to imagine an electron doing this super fast, non-stop hop from one iron atom, the Fe2, across that bridge over to the other one, the Fe3.
So let's just trace this process step by step. First, you've got our pair of different iron atoms. Then, you've got that electron that is just constantly hopping between them. And this tiny action, this little electronic dance, is perfectly tuned to absorb energy from a very specific type of light, and that is what creates the color we see. And what type of light are we talking about? It's light with a wavelength right around 700 nanometers. Now, that's in the red-orange part of the spectrum. So, when light hits the crystal, all that hopping just soaks up the red and orange light. And think about it. If you take the red light out of white light, what color is left for our eyes to see? That brilliant, deep Prussian blue. So the main takeaway here is this. The electron hop is the color.
Okay, so we know the special pair of two different iron types, plus that electron hop between them is what creates the color. So, how do you turn the color off? It's actually pretty simple. You have to break the pair.
You just break the pair. I mean, if the color depends on having both FeA and Fe3 right next to each other, then the mission is to make all the iron atoms the same. If you can do that, you turn off the blue.
And we do that with a little jolt of electricity. This equation here shows the first way. We add an electron, that's the little E negative symbol, to our Prussian blue. That negatively charged electron gets snapped up by a positively charged Fe3 atom, which turns it into an Fe2. And once they're all Fe2, the special pair is gone, and we're left with a colorless material called Prussian white.
Now, this whole process can actually go in two directions. On the left, we've got what's called reduction. We add an electron, which changes all the Fe3s to Fe2s. The pair is broken, and the crystal turns clear. But we can also do the exact opposite, which is called oxidation. See on the right? You apply a different voltage to remove an electron. This turns all the Fe2s into Fe3s. And once again, the pair is broken, that absorption band vanishes, and the color is erased, this time leaving behind a kind of yellowish-brown color.
But hold on a second. There is a hidden player in this game that is absolutely critical. We've been talking all about electrons moving in and out, but we've missed a really crucial piece of the puzzle.
Just think about this for a minute. We're pumping negative charges, electrons, into this solid crystal. Now, if that's all that happened, the crystal would build up this massive negative charge, and that's just not stable. So how does the material stay perfectly balanced?
Well, the answer is something else has to move in to cancel out that charge. For every single negative electron that enters the crystal, a positive ion from the liquid around it has to move into the crystal too. This whole process is called charge compensation, and you know what? It's essential for the color change to even happen at all.
And it turns out there is one particular ion that is absolutely perfect for this job, potassium, which we show as K+. But why? I mean, out of all the ions out there, what makes potassium the star of the show here?
The reason is all in the crystal's physical structure. Scientists call it a zeolitic framework. The best way to picture it is like a microscopic, rigid sponge. It's a solid, for sure, but it's filled with these tiny, precisely sized channels running all the way through it. And just like with a sieve, size matters a lot. Only a few positive ions are the absolute perfect size to zip through these channels quickly and easily. This list here shows the best ones. Ions like rubidium and cesium, they also work. But right at the top of the list is potassium. It's kind of like the Goldilocks ion, not too big, not too small. It is just the right fit to let the color switch happen fast, stay stable, and be completely reversible.
Okay, so we've looked at where the color comes from, the electrical switch that turns it off, and the hidden key, that potassium ion that makes it all work. Let's put every single piece together now and look at the full picture.
This quote from the source material just summarizes the entire thing perfectly. Let's break it down real quick. Electrochemical toggling of Fe oxidation states. Yep, that's us using voltage to change the iron atoms. Where ion insertion maintains electron neutrality. That is our potassium ion buddy moving in to keep the charge balanced. And the result? The color changes because that special IVCT band appears only in the mixed-valence state, which just means only when we have both types of iron. That's the whole story.
And this simple chart shows the final result. Just look at the bar for that key 700 nanometer light absorption. In the Prussian blue state, it's high. The switch is on. But for both Prussian white and the oxidized form, that absorption is totally gone. The switch is off. The color change is literally a toggle switch for that specific band of light.
So, what we have here is a material whose color can be perfectly controlled with just a tiny electrical signal, all thanks to this beautiful dance of electrons and ions. And that brings us to the final really big question. What's next? What can we build with this? Smart windows that tint themselves on command? Ultra-low power displays? The ability to switch a material's most basic properties at will, it opens up a whole new universe of possibilities.